Hello, this is a presentation on NEOS 2 processor instruction set implementation, which was done using Verilog. This is a EE275 computer architecture term project done under the guidance of Dr. Chang Chu. What are the objectives of this project? Implementation of a subset of NEOS 2 instruction set architecture. 5-stage pipelining is used in this project. Dot product and factorial benchmark programs are implemented in Verilog. Instruction and data memory are initialized with the program and data in the test bench for the Verilog program. And finally, the display of output of the dot product of the two vectors is done, and the 5 factorial answer is displayed. Now let's see what exactly are the features of the NEOS 2 processor. It is a general purpose RISC processor core with features like full 32-bit instruction set, data path and address space. There are 32 general purpose registers as well as some optional shadow register sets present. There are 32 interrupt sources. There are dedicated instructions for computing 64-bit and 128-bit products of multiplication. Along with this, there are a variety of on-chip and off-chip peripherals present. These are just few of the features of the NEOS 2 processor. Now see the instruction set of this processor. The instruction set is divided into 3 types of instructions: the I type, the R type, and the J type. This shows how each of these instruction bits are divided into segments like opcode, immediate value, source bit, destination bit, and target bits. Now let's move on to how the architecture of this processor looks. Here we can observe that the PC output goes to the instruction memory register, which is a 32-bit memory register, as well as the output goes to the next register where the PC is incremented by 4. The next stage after the instruction memory is the register file, where the instruction is decoded and the reading of the two registers is done, as along with write register and write data lines present. Here the checking of the branch, that is the condition, is done whether the branch condition is satisfied or no. After the register file, the line follows back to the ALU unit where the ALU operations are done, like multiplication, addition, division, etc. The ALU unit is controlled by the ALU control. Finally, the output from the ALU is given to the data memory, where the data is either read or written to the memory. And the final stage of the architecture is the write back stage, from where after the memory access, the data is written back to the instruction memory and the cycle of the 5-stage pipelining is completed. Along with this, there is a sign extend unit present as well in the architecture. The architecture is implemented in such a manner that there are buffers present between each stage of the pipeline. The 5 pipeline stages are the fetch stage, the decode stage, the execute stage, the memory access stage, and the write back stage. In the fetch stage, the instruction is fetched, which is present in the queue. The PC, that is a program counter, is incremented by a value of 4, and the next instruction is being fetched simultaneously. After the instruction memory, the instruction is decoded in the decode stage. Here the register values are read from the register file, and also the checking for the branch is done in this stage. The next stage comes the execute stage, where the operations or the instruction is executed, whether the ALU operations are done on these instructions, and the output from the ALU is given to the memory access, where if there is a need to read the data from the memory or to write the data into the memory. This is done using instructions like load and store. And finally, after the memory access stage comes the write back stage, where the final output is then written back to the registers. That is, the registers are then upgraded with a new value after the result of that instruction. This is exactly how the implementation is done in the Verilog. This is the benchmark.product program we can see here. These are the assembly instructions or the instruction set according to the Nios 2 processor, with the type of each of them given here in the table, and the opcode for each corresponding instruction is shown here as well. So basically what happens in the dot product is there are two vectors, the vector A and vector B, with elements in each of the vectors whose output is multiplied, and the final output is shown, which is saved in the result register. Now let's see how the timing diagrams of the Verilog program after simulation have come out to be. The result for the vector A and vector B has been shown here in the timing diagram as 580, which is stored in a register called as the ALU result execute, which is a 32-bit register. Here in this particular timing diagram, we can see how the pipelining has been verified using Verilog. That is, in each cycle, a different stage of the pipelining is executed. The execution stage is followed by the memory access stage, followed by the write back stage, etc. Next is how in the fetch stage we can see that the program counter as well as the next program counter is incremented by a value of 4 in each cycle. In the memory read and the memory write stage, we can see here that whenever the memory is 1, the data is read from the memory as well as written into the memory. So after the data being read here in the cycle, in the next cycle it is being written to the memory, and the cycle goes on for whenever the memory read is 1. These are timing diagrams for the ALU operations, which we can see. Here we can see that the multiplication of each corresponding element of the vector, the operand 1 holds the vector elements for vector A, whereas the operand 2 holds the vector elements for vector B. These two are multiplied and the result is then saved into the result register, which is a 32-bit register. Addition. After the multiplication of each corresponding elements of the two vectors is done, the addition, the result are then added correspondingly, and finally the addition is saved in the result vector again. Stalling. What happens to stalling is that the processor stalls for that particular time whenever the signal is high. So it retains the value of the previous cycle. Thus, when the stall is high, we can see that there is no change in the values, and the values are being carried forward till the stall becomes low back again. Stall happens due to various reasons, various hazards, which can be differentiated into 3 hazards like the control hazard, the data hazard, and the structural hazards. These hazards were detected and as well as resolved in the Verilog implementation. Now let's see the factorial program. This program is where the 5 factorial is being computed. Again, the table shows the assembly level instructions, the type of instructions, as well as the opcode for each of them. So we see that after the program has been implemented for 5 cycles, the output which we get is 120 in the final ALU register, which is again a 32-bit register. Thus, we can see that Verilog was used to test the correctness of the Nios 2 processor using the programs like the benchmark, programs like dot product and factorial. So we can conclude that the testing was successfully done using Verilog. Timing diagrams for the 5-stage pipelinings were simulated as well as studied. The working of the 2 benchmark programs was studied using Verilog. Forwarding was implemented successfully in the program, and the hazards, as explained, were detected and resolved in the project. So these are the references with which the program and the project was implemented. Thank you.